Hi everybody, welcome to physics. It's Mr. Duffy. Today we're going to be talking about a special type of friction called air resistance. So it's friction forces with air molecules. We've been talking about friction in our previous lessons. So again, the concept is not really new. Friction here is being caused between the air molecules moving past whatever object is moving through it. And that, again, interaction is causing the friction. But again, we're going to go into that a little bit deeper when we're talking about, again, air resistance. And we're going to talk about a special concept where air resistance equals the weight of the object, in which case we would reach what's called terminal velocity. So let's go ahead and get started on this concept. So I know we've talked about free-falling objects in previous lessons, previous units even, and we talked about how it's when an object is falling under only the influence of gravity. But we haven't really talked about what is going on with those forces or why they're all falling at the same rate. Again, that constant rate of acceleration of gravity of negative 9.81 if we're on the Earth. Well, the reason why is because the Newton's second law, F equals ma, sets up a ratio where the acceleration, again, is constant. The ratio of the force of the falling object, the weight of the object, is equal to the mass. So that ratio always stays constant no matter, again, what the objects are. So here's an example of this. Again, since the acceleration due to gravity is a constant value, it's always negative 9.81, again, it's relating the force of the object, the amount of weight of the object, to its mass. And if the force is small, its mass is also small. Again, it gives you a constant acceleration. If it's like in between, the force is medium and the mass is medium, its amount of matter is in medium. If the force of the object is large, the force of gravity pulling down, again, is large, then again, its mass is going to be large as well. And so, again, since that kind of works out for like a small object, a medium object, a large object, a heavy object, since that ratio, it's a ratio, the acceleration is always coming out to that constant value of the negative 9.81. Okay? Now, this again is only in a vacuum. So in the absence of air resistance, gravity is the only thing that's affecting the object. Objects still have, again, weight from gravity pulling it down, and all objects fall with that same rate because, again, it's a ratio of the weight to its mass. So again, that's in the absence of air resistance, and that's what we've been doing in previous units, previous lessons, and so forth. We've ignored air resistance and whatnot, and we just use gravity. Now, this video here, we'll talk about that. It's kind of cool. They drop objects in a vacuum chamber. Take a look at that. It's fun to watch. Or again, you kind of skip through that part of the concept. But again, it's kind of an interesting video. Now,
this is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left. And it's kind of got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems, and that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, the strongest material to build a vacuum chamber out of. So they built an outer concrete skin, which is part radiation shielding and part an external pressure vessel, so that this thing can take the force that's present on the outside when it's pumped out to the conditions of outer space. Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest. Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So in order to see the true nature of gravity, we have to remove the air. It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
Okay, we dropped 2 millitorr in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. PCV 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
Look at that.
They came down exactly the same. Wow.
Look.
Watch right there. Look at how they hit right there.
Exactly.
You're back on the side.
Exactly the same.
Feathers don't move, nothing.
Look at that. That's just brilliant. Isaac Newton would say that the ball and the feather fall because there's a force pulling them down. Gravity. But Einstein imagined the scene very differently. The happiest thought of his life was this. The reason the bowling ball and the feather fall together is because they're not falling. They're standing still. There is no force acting on them at all. He reasoned that if you couldn't see the background, there'd be no way of knowing that the ball and the feathers were being accelerated towards the Earth. So he concluded they weren't.
When objects are not in a vacuum, which is 99% of the time, right? So air will stop the object's acceleration. And this is where we reach what's called the concept of terminal velocity, the speed at which the air resistance, the force of friction, is balancing out the object's weight. Now, this is the maximum speed in which an object can actually obtain while falling through the air. Different for different objects because different amounts of friction and so forth, or different forces from gravity, but again, all objects will kind of reach this terminal velocity at some point in time where the forces again balance out and the accelerations again is zero, moving with a constant velocity. Still falling towards the ground, it's just air resistance has balanced it out. Okay? Now, another way we can say this is when we're talking about like net forces, the net force is zero because the weight minus the air resistance equals zero. Terminal velocity has been reached. Now, this video deals and talks about what terminal velocity is, and it goes through a very common example. This would be somebody skydiving. So a skydiving example, we have air resistance pushing back up, the person's weight, again, pushing down. At some point in time, again, you want to increase your air resistance, so you deploy your parachute, and again, you reach a new terminal velocity. So while you're falling without the parachute, you're reaching a terminal velocity. At some point in time, when you deploy your parachute, that again slows you down. You have a lower terminal velocity, and that allows you to land safely. So again, the concept there in the video, and that is terminal velocity. So hopefully after watching this other second video, you understand what it is and why it's important. And thank you for watching.
You might be wondering why I'm sat in the door of a plane strapped to someone who can only be described as a madman. Frankly, at this moment, I was asking myself the same thing. I'm Ross, and this week we're exploring the science of skydiving. So how is it possible to jump out of a plane and survive? Gravity is a pretty powerful force, and 15,000 feet is a long way to go before hitting the ground. We've all experienced gravity. What goes up must come down, and it's a product of the object's mass. This apple and the Earth are both being attracted towards one another because of the force of gravity. But since the apple is far less massive than the Earth, the apple appears to fall towards the Earth. The acceleration due to gravity is 9.8 meters per second per second. In other words, with each second that passes, I'm going to be traveling 9.8 meters per second faster. But this doesn't mean that I'm going to keep speeding up until I hit the floor with a splat. So here I have a giant fan and a smoke machine. Now, if I take this inflatable shuttle and place it in the stream of air, we can see that it flows over it very easily. So there's not much air resistance there. But if we switch this to something with a bit more surface area, we can now see the air is a lot more turbulent and is facing greater air resistance. This air resistance is what's going to help me survive the jump. As I fall through the air, it's going to be pushing back on my body in the opposite direction. And the faster I fall, the greater the force of air resistance pushing back. After 3 seconds, our speed is already at 60 miles per hour, but air resistance is already affecting our acceleration. By 8 seconds, we're at 102, and it takes a further 7 seconds for us to reach 120 miles per hour. At this point, the force of gravity is equal to the force of air resistance. This means that we've stopped accelerating, and so our speed is constant. This is called our terminal velocity. This belly down position also helps increase air resistance, but even so, hitting the ground at 120 miles per hour is still a very bad idea. The instructor has already released a small parachute which helps create a little extra drag. When we get to roughly 3,500 feet, the instructor deploys the main parachute. All of a sudden, the huge surface area massively increases the air resistance and we quickly decelerate. In just a couple of seconds, we go from 120 miles per hour to just 5. And I've got to tell you, that's the biggest wedgie you can ever experience. After several minutes of gliding around, we land safely back on Earth. For more science stunts, why not watch me walking across red hot coals? Stay tuned over the next few weeks as we'll be investigating all things foodie, from beehives to milking cows. So for more science every week, click subscribe. Thanks for watching.